All right, guys, today we are on our third part of Module 4, Dynamics Part 3. The objectives for today's lesson are going to be, first off, to discover what free body diagrams are. All right, so we're going to actually discuss what they are, why they're useful, and what they need to include. Then we're going to begin drawing free body diagrams, so we're going to go through kind of like a step-by-step process for what you kind of need to think about in order to be able to draw your own free body diagrams. And then we're going to move on from that, and we're going to start talking about tension in flexible cables. So tension is going to be kind of one of the more awkward topics in the Intro to Dynamics module. So we're going to talk about that today. First off, what are free body diagrams? Well, what you see here is basically an example of a free body diagram. All that a free body diagram is it's taking a real-world object, a single real-world object. It is going to basically sketch it in a very simple way on paper. And then it's going to sketch the forces that are currently acting on it. So what I'm saying here is that whatever the object is, however complex it may be in the real world, we're going to go ahead and sketch a very simple version of it. It could be just a square, a box, or just like a single point on a page. And then we're going to go ahead and actually sketch arrows, each arrow representing every force that's acting on it. So each arrow represents a single force, and we want an arrow for each force that's acting on the object. If we're able to do this and label each force, then we basically have a free body diagram. When you're drawing your own free body diagrams, you want, to the best of your ability, to label everything clearly. All right? Use conventions when you're labeling things, like if it's force due to gravity, use F sub G. If it's normal force, use F sub N, things of this nature, so that everybody can read your free body diagrams. And then, if at all possible, you want to actually label the magnitudes of your forces. Okay, so if you have every force that is acting on an object labeled with magnitudes as well, then you've pretty much completed a full free body diagram for the scenario. All right, free body diagrams help us to solve problems, especially when there's trigonometry involved. So what I want to do is I want to actually show you an example of a free body diagram I wrote for you the other day. I didn't call it a free body diagram at the time, but now that we're introducing free body diagrams, I want to tell you that this indeed is a good example of a free body diagram. And the reason that I like this one is because, while of course I do show and label the three forces acting on the single object, which I just sketched as a point, the bobsled, I also showed you the resultant force. All right? And so that's actually a very good thing to add onto your free body diagram, if at all possible. Now, there's another aspect of this free body diagram that I want to point out. That purple resultant force vector is longer than the applied force vectors. All right? That's on purpose as well. To the best of your ability, you want to actually give a length to your arrow vectors that kind of are proportional to the magnitudes of your vectors. So if one vector is clearly larger in magnitude than the other vectors, then that vector should clearly be longer as an arrow in your free body diagram. Does that make sense, guys? All right, there's another aspect of this free body diagram that I really like. I'm actually showing you the angles. Of course, I don't have the values for these things in this free body diagram, but I do know that they are going to be applied at some angle. And if at all possible, I'm going to label those angles and give the magnitudes of those angles. That should give you all the information that you need in order to find things like the components of these vectors. Does that make sense to you guys? Awesome, awesome. So when you're drawing your own free body diagrams, we're going to basically go through a couple of steps. First, you need to decide exactly which object you're drawing a free body diagram of. There should only ever be a single object in a free body diagram, but here's the weird thing. That single object can be the sum of multiple objects, right? Okay, so I'll show you what I mean in a little bit. But either way, whatever free body diagram you're drawing, you need to be only focusing on a single object. Then you want to actually sketch that object. It can be just a simple shape. Even if we're talking about a boat, we still want to sketch a very simple shape for our free body diagram. Could be a square. In the practice problems, there's one I do as a circle. A lot of times I use a single point. Okay? Then we want to make sure we know and can conceptualize every single force that might be acting on that object. A lot of times it's going to be force due to gravity. Sometimes it will be the normal force. Sometimes there will be tension force. Sometimes it will be applied force. Sometimes it will be friction force. Okay? Make sure that you are able to identify every single force that might be acting on that object. And then you want to actually sketch vector arrows on your free body diagram to represent each of those forces. Remember that your arrow should point in the correct direction that the force is being applied to, and it should be have a relative length that represents the magnitude of your vector. So the vectors with the larger magnitude should have longer arrows. Lastly, you want to make sure you do your best to label each force. Like I said, if at all possible, give the magnitudes as well, but make sure they at least have a name, like F sub G, F sub N, F sub T for tension. Okay? So, let's actually look at a problem that would benefit from us drawing a free body diagram for. Imagine that we're pulling a 10 kilogram box by a string along a smooth surface. I really want to highlight one term here, smooth surface. In AP Physics, we don't always neglect friction. In fact, the next lesson is going to be all about friction. All right? So that means it's important for us to be able to identify when a problem doesn't want us to consider friction. And this is the #1 most used term for letting you know that you should not consider friction, a smooth surface. All right? So imagine pulling a 10 kilogram box by a string along a smooth surface. The magnitude of the applied force, which you'll see it's this applied force right here, the magnitude is 40 newtons, but at 30 degrees to the horizontal. All right? We want to calculate the acceleration of the box, and we want to calculate the magnitude of the normal force. Now, if you remember from the last lesson, we introduced normal force as the force that counteracts gravity when an object is sitting on a surface. Okay? Usually, if there's no other forces acting on the object, the normal force is equal and opposite to gravity. But when we start throwing in different forces, that can affect the magnitude of the normal force. So you're going to see in this problem that the normal force is not equal to the magnitude of gravity. Okay? And I'll spoil it for you. That's simply because the box is being slightly pulled up by the applied force. And so that's affecting how much force is required to keep it in balance. Now, first off, let's see if we can calculate the acceleration of the box. Before we start that, this lesson is all about free body diagrams, so let's sketch our own for this situation. All right? So, an FBD for this situation might look like this. I might decide to use a box, and I'd say that this box is my object. All right? Make sure I know that this box is 10 kilograms, but it doesn't have to be labeled on your free body diagram. Now, anybody want to tell me one of the forces that might be acting on this box right now? Go ahead. Gravity, right? So what direction is gravity going to be pointing? Downward. Yeah, downward. Awesome. So that's going to be a downward force. Trying to make this pretty for you guys. And we're going to label it F sub G. All right? Do we know what the magnitude of gravity is right now? Can we find it? How would we find it? Go ahead. Go ahead.
Mass times acceleration.
Mass times acceleration, and we know both of those, right? All right, so I'm just going to go ahead and say this would be equal to the 10 kilograms times 9.8 meters per second. Does that sound okay to you guys? Meters per second squared, sorry. That'll give me 98 newtons. Anybody disagree? All right, cool. So I labeled that vector fully. Now, what are some other forces that are acting on this box right now as it's sitting on a table? All right. So like just to show you also that it's sitting on a table, let's make that right. Okay. What else do we got? Go ahead. Yes, a normal force coming up from the table. So that is going to be directed opposite to the force of gravity. But I gave you a heads up beforehand that it's not necessarily equal to the force of gravity, but in this case it is still opposite in direction. So I don't yet know what the magnitude of the normal force is, so I'm just going to leave that be for now. And then there's going to be at least one more force acting on this, am I correct? Can somebody tell me? The applied force? The applied force, fantastic. So if I'm going to zoom in here a little bit, it should be easier for me to give my applied force. I'm going to make it a vector just like this, all right? And I'm pointing it up kind of like diagonally because I know that it should be at exactly 30 degrees from the horizontal. Everybody agree? All right, and we know what the magnitude of this one is, right? 40 newtons. Now, if we could give one critique to this free body diagram right now, it would be that it looks like my applied force, it looks like the magnitude of my applied force as shown by the length of the arrow is a little bit too big. Do you guys agree? right? Because if we're comparing it to the applied force of gravity and the normal force, it should definitely be smaller, like by more than half actually, right? But I've drawn it this way just so that it's easier for us to see. In reality, the arrow for the applied force should be smaller. Either that or the arrows for the applied force of gravity and normal force, the arrows for the gravitational force and normal force should be bigger. All right, so now we've given our free body diagram, and this should help us to see that the force, our applied force of 40 newtons, must have some vertical component in this direction and some horizontal component in this direction. Do you guys agree with me? Good. So then this is me telling you now that that vertical component of this applied force is going to be directly counteracting gravity. Not entirely, but it will be going against gravity. Do you agree? Fantastic. So it's going to be important for us to find the magnitude of that vertical component so that we can see how much downward force is really being applied to the table. And that's how we're going to find out what the normal force is. Okay, but at the same time, we need to find out what the acceleration of this box is. Okay, so can anybody in here right now tell me what direction is the net force on this box?
To the right?
To the right is absolutely right. A lot of you guys were just pointing, but yes, you're right. To the right. And the reason for that is the force due to gravity should be being canceled out by the normal force and the vertical component of our applied force. So the only force that's not being canceled out by anything is the horizontal component to our applied force. Does that make sense, guys? So that means whatever this guy is right here is going to be our net force. It's the only thing not being canceled out by anything. So let's go ahead and try to find that net force. I noticed that that horizontal leg is adjacent to my angle of 30 degrees. Yes, sir? Sorry? Cosine? Yes, cosine. So if I want to find that, let's call our applied force F sub P. And if I want to find the horizontal component of that applied force, I'm just going to label it F sub Px. All right? I know, based off of the right triangle trigonometry, that that must be equal to the magnitude of the applied force times cosine of 30 degrees. All right? Cosine of 30, what is that one? Root 3 over 2? Yeah, root 3 over 2. So that should be 20 root 3. Okay. That should be equal to about 20 root 3. We just need a decent approximation, so I'm going to pop that into the calculator really quick. 20 times root 3. Looks like it's about 34.6. That will be in newtons. All right. Great, so now we have the net force. Remember, we decided that this was the only force that wasn't being counteracted, so it must be the net force on the object. If we have the net force, which one of Newton's laws can we use to find the acceleration? Go ahead. F equals ma, that's absolutely right. So we're going to use Newton's second law to find the acceleration that the box is experiencing right now. And we're going to go ahead and plug in that 34.6 newtons as our net force. 34.6 newtons must be equal to 10 kilograms times acceleration. Alrighty? So if I divide both sides by 10 to isolate my acceleration, then I'm going to get 3.46 meters per second squared is equal to A. So that's the answer for A. All right, and we all know, of course, that newtons divided by kilograms leaves us with meters per second squared, correct? Fantastic, fantastic. So we can now say as a statement that this box must be accelerating to the right at an acceleration of 3.46 meters per second squared because of the fact that there is a 34.6 Newton net force to the right due to our applied force of 40 newtons at 30 degrees to the horizontal. A lot of words there, but hopefully they all made sense. Now, next step, what is the normal force? Okay, it's pretty simple, guys. The vertical component to our applied force is going to counteract part of the force due to gravity. Whatever's left over as a net force downward is going to be counteracted by the normal force, and that's how we're going to find our normal force. But first, we need to go ahead and take a moment to find our FPY. And since we used cosine to find FPX, we're going to use sine to find FPY, the vertical component of our applied force, and that's going to be equal to 40 sine 30. If you guys have had pre-cal or calculus already, you should know sine 30 right off the bat is just 1/2, correct? All right, so sine 30 is 1/2 times 40. That should give us 20, all right, 20 newtons. All right, That's going to be the vertical component of our applied force. So basically we're pulling it with 20 newtons of force directly upward, while gravity is pushing it down with 98 newtons. Those are going to be canceling each other out to a certain extent. So all we're going to have left in our downward force is 78 newtons of downward force. All right. So if our downward force is 78 newtons, then the normal force must be 78 newtons to counteract it. So in this case, our normal force finally should just be 78 newtons. All right. Hopefully, through this example that had multiple steps, you can see why drawing your free body diagram beforehand and using it to actually work through the problem is very useful. All right, good, good. Let's go ahead and move on to tension. Anybody have any questions before we do that? Tension is a little bit of a weird thing. Let's talk about it. So tension in a flexible cord, like a rope, a string, or even a cable that you use to charge your phone, exerts a force when you pull it tight. Okay, let me actually grab this cable that I'm using to charge my iPad. It exerts a force when you pull it tight. So right now there's no tension, right? But the moment that it becomes what we call taut, the moment it becomes taut, like fully stretched out, then it starts to exert some force. All right, that force is called tension. And I can feel the force right now. I can feel that the force on my right hand by the cable is being pulled in this direction. And also, on my left hand, I can see that it's being pulled in this direction. For both hands, I can feel the cable pulling inward because it doesn't want to be pulled outward. All right. So this force is called tension. It's going to be equal on my right hand as it is on my left hand. So right now, my right hand and my left hand should be experiencing an equal force by this cable. All right, and that force is going to be the force of tension. If I were to grab this cable at any point, the tension doesn't change, okay? If I were to pull with the same force, then the tension I feel at every point should be equal. Does that make sense to you guys? Right? So it doesn't matter where I'm grabbing it. The tension is the same. All right? And if I were to measure the tension force at any point in between my hands right now, it would be basically the same pointing in both directions, right? Because on this end of the cable, the tension force is pointing that way. And on this end of the cable, the tension force is pointing that way. All right? At every point in this cable, the tension force is pointing in both directions. That's a little bit of a weird one to consider, but we're going to see an example in our practice problems that kind of like illustrates that a little bit better for us. Let's continue. This purple line is very important. Tension always acts along the direction of the cord and pulls equally in opposite directions at any point on the cord. That's exactly what I was trying to just tell you right now. All right, but another important thing to understand is that the tension is always pointing along the direction of the cord. That said, let's go ahead and try to consider a problem that actually starts to implement tension. Consider this system, okay? You're about to hear me say the word system a lot more. And when I say system, I mean some type of dynamics problem that has more than one object, okay? Good, so we have a system here in which we're actually pulling the entire system to the right using a force of 40 newtons, an applied force of 40 newtons. Everybody can see this, correct? So this 40 Newton force, assuming this is a smooth surface, will definitely be enough to apply some acceleration to this system. All right? What acceleration is it going to apply? Okay, this string can't be stretched any further than it already is. It's going to already start to apply some tension to both of the boxes. But just considering we're pulling from this end, how can we find the acceleration that the system experiences? Is it any different than what we've done before? Just F equals ma. So let's go ahead and find out what acceleration this system is going to experience. It must just be F equals ma. Let me use green here. F equals ma. The force is, the net force that's given is 40 newtons, correct? So 40 newtons must be equal to, what's the mass? 22, yes. We're going to take the mass of the whole system. 22 kilograms. And that should give us our acceleration, okay? So then I can say that A must be equal to 40 newtons divided by 22 kg. All right. I'm not sure what that is right off the top as far as the decimal is concerned, but it's close to 2. 40 divided by 22, 1.8. All right. So this should give us an acceleration of 1.8 meters per second squared. Now bear with me, guys. That is going to be the acceleration that both of these boxes are going to experience because we just took the acceleration of the whole system. All right. If I was going to draw a really quick free body diagram for the system, I would use 1 point to represent both boxes. And that's what I meant earlier when I said 1 point in a free body diagram could represent an entire system of things. Okay. But as long as you're considering that 1 point to have the mass of the whole system. Make sense, guys? Good. So I can say that, yes, there's some F sub g going down. There's some F normal going up. We're not concerned with those right now, but what we are concerned with is the applied force to the right of 40 newtons, right? So this would be a free body diagram for both boxes. Now, moving forward, it's asking the slightly more tricky question, what is the tension in the cord that's connecting the two boxes? All right. Now, hopefully, I can explain this very simply. If this hand was the front box and this hand was the back box, then the force of tension must be however much force is required to pull the back box at an acceleration of 1.8 meters per second squared. I can run that back one time for you guys if you need me to. All right, cool. So let me actually use the same orientation as the photo. All right, so from your perspective. This hand right here is the 10 kilogram box. Are you with me? This hand right here is the 12 kilogram box. You with me? All right, so there's going to be a force applied in this direction that's going to cause both boxes to accelerate in this direction. Then, we know that that force was 40 newtons to move the whole system, correct? All right, you see this motion? This is at rest, and then after the force is applied, right? Okay. Whatever tension is in this cable that's connecting the two boxes, whatever force of tension, it must be the force required to move 12 kilograms at an acceleration of 1.8 meters per second. Make sense? That's it. That's all there is to it. All right, because we know that force of tension is equal at every part on the cable. So whatever force that cord is applying to the 12 kilogram mass must be enough force to move it at 1.8 meters per second squared, because that's what we decided was the acceleration that it experiences. So let's do that really quick. Whatever the force of tension is, F sub t, it should be equal to 12 kilograms times 1.8 meters per second squared. All right, let me pop that in. That gives me a force of 21.6 newtons. And that should be the force at every single point on this cable, especially the point here where it's pulling in this direction. Yes, sir?
Say there's a third box connected. Does that same cord, does that still have the same does that have the tension compared to that second box that you added?
So if there was another mass to the left of this, the tension on this cord, the way we'd find it would be the same, but we would have to consider the mass of this system right here.
And then if you want to find for that second cord over there, is it just that one box over there?
Yeah, if we wanted to find the tension force for this cable, we would just consider the mass of the last box. Make sense? We're going to elaborate further on a couple of different weird tension situations on the practice problems. But that's all here. Are there any questions before we end the lecture? Good job, guys. All right. Now, you're going to find that there are 9 practice problems. All right. Video solutions for those are already posted. So go ahead and attempt them on your own. But if you get stuck, the solution's already posted.